Hey there, and welcome back to Code Canvas. Today, in linear and binary search, we're diving into linear and binary search. Let's jump right in.
Today, we're diving into the fundamental computer science problem of searching. Imagine you have a list of items, and you need to find a specific one. How would you do it efficiently? Think about finding a specific book in a library. If the books are scattered randomly, you'd have to check each shelf, one by one, until you stumble upon the book you're looking for. In computer science, this list of items is often an array, and finding a specific item means searching for a target value within that array. This is a very common operation. The way we search significantly impacts how fast our programs run, especially with large amounts of data. An inefficient search can bring a powerful computer to a crawl. Let's start with the most straightforward approach, linear search. It's like checking every book on every shelf, one by one, from left to right, until you find what you need. Here's an array of numbers, and our goal is to find the number 12. With linear search, we simply start at the beginning of the array. We compare the target, 12, with the first element, 23. They don't match, so we move on. This is a direct sequential check. Next, we check the second element, 5. Still not a match. We continue this process, examining each element in order. We move to 8. No match. The pointer simply advances, step by step, through the array. This is the core logic of linear search. Finally, we reach the element 12. It matches our target. We've found it, and the search can now stop. Success! What if the target isn't in the array? Linear search would continue checking every single element until it reaches the very end. Only after exhausting all elements would it conclude that the target is not present. This exhaustive scan is the defining characteristic.
So, how efficient is linear search? In the worst-case scenario, we might have to check every single element in an array of n elements. This means its time complexity is proportional to the number of elements, n. We express this using big O notation as O of n. O of n implies that if you double the size of your array, the time it takes to search could also roughly double. It scales linearly. The main advantage of linear search is its simplicity and that it works on any array, whether it's sorted or not. No special preparation is needed. However, for very large datasets, O of n can become extremely slow. Imagine searching through 1 billion items. That would take 1 billion steps in the worst case. So while linear search is simple and versatile, its performance can be a significant bottleneck for larger applications. There must be a better way. What if we could use some extra information about our data to speed up the search? What if our data was already sorted? This brings us to binary search, a powerful and highly efficient algorithm, but with a crucial prerequisite: the data must be sorted.
Imagine looking for a word in a dictionary. You wouldn't start from the first page and scan. Instead, you'd open it roughly in the middle. Binary search follows this exact divide and conquer strategy. It repeatedly divides the search interval in half. This is its core intuition. Let's use our sorted array with 2, 5, 8, 12, 16, 23, 38, 56, 72, 91. We want to find 12 again. We'll track 3 pointers: low, high, and mid. Initially, low points to the first element, index 0, and high points to the last element, index 9. These define our current search space.
Next, we calculate the mid-index. It's simply low plus high divided by 2. In this case, 0 plus 9 divided by 2 gives us 4, integer division. Now, we compare our target, 12, with the element at mid-index, which is 16. If ARR at mid equals target, we found it. In our case, 12 is less than 16. Since the array is sorted, we know our target must be in the left half of the current search space. So we update high.
We set high to mid minus 1. Now our search space has shrunk dramatically, from indices 0 to 9 to just 0 to 3. We've eliminated half the elements. Conversely, if the target were greater than ARR mid, we would update low to mid plus 1, searching in the right half. This is the divide step. With the new low and high pointers, we repeat the process. Calculate a new mid for the reduced range. This iterative refinement is key. Our new low is 0 and high is 3. Mid becomes 0 plus 3 divided by 2, which is 1. The element at ARR 1 is 5. Target 12 is greater than 5, so we update low to mid plus 1, making low equal to 2. Our search space narrows even further.
Now, low is 2 and high is 3. Mid becomes 2 plus 3 divided by 2, which is 2. The element at ARR of 2 is 8. Target 12 is still greater than 8, so low gets updated to mid plus 1, making low equal to 3. The search range is now just 3, 3. One last iteration. Low is 3, high is 3. Mid becomes 3 plus 3 divided by 2, which is 3. The element at ARR of 3 is 12. Bingo! Our target 12 matches ARR of mid. We found the target in just 4 comparisons, compared to 4 in linear search for this specific case.
The real power of binary search becomes evident with much larger arrays. Each comparison effectively halves the remaining search space. This repeated halving leads to a logarithmic time complexity. We denote this as O of log n. This is incredibly efficient for large datasets. To illustrate, for an array with 1 billion elements, 10 to the 9th, linear search might take 1 billion steps. Binary search would find it in about 30 steps. That's the enormous difference between linear and logarithmic growth. Binary search is a game changer for searching in sorted collections.
To summarize binary search, it requires sorted data, uses a divide and conquer approach, and repeatedly halves the search space to achieve O of log n efficiency. Now let's look at a typical iterative implementation of binary search in code. We'll use Python for clarity, but the logic applies universally. We start by defining the function binary search, which takes the array R and the target value as input parameters. Inside the function, we initialize our low pointer to 0, the first index, and high pointer to len of R minus 1, the last index. The core of the algorithm is a while loop that continues as long as low is less than or equal to high. This means our search space is valid. Inside the loop, we calculate the mid index. Using low plus high minus low divided by 2 prevents potential integer overflow compared to low plus high divided by 2 for very large indices. First, we check if the element at mid is equal to our target. If it is, we've found our item and simply return the mid index. If ARR of mid is less than target, it means the target must be in the right half of the current search space, so we update low to mid plus 1. Otherwise, if array of mid is greater than target, the target must be in the left half. We update high to mid minus 1 to narrow the search. If the loop finishes and low becomes greater than high, it means our search space has become empty. The target was not found, so we return -1. Let's trace this code with our example array 2, 5, 8, 12, 16, 23, 38, 56, 72, 91, and target 12. Watch how low, high, and mid move. Initial state. Low is 0, high is 9. The entire array is our search space. Mid is calculated as 0 plus 9 divided by 2 equals 4. At mid, we have 16. Our target 12 is less than 16, so we update high to mid minus 1, making high 3. New iteration. Low is 0, high is 3. Mid is 0 plus 3 divided by 2 equals 1. At mid, index 1, we have 5. Target 12 is greater than 5. Since target is greater, we update low to mid plus 1, making low 2. The search space is now 2, 3, elements 8 and 12. Next iteration. Low is 2, high is 3. Mid is 2 plus 3 divided by 2 equals 2.
At mid, index 2, we have 8. Target 12 is greater than 8.
Again, target is greater, so low becomes mid plus 1, which is 3. Now low is 3 and high is 3. Our search space is just one element. Final iteration. Low is 3, high is 3. Mid is 3 plus 3 divided by 2 equals 3. At ARR of 3, we find 12. It matches the target. The function returns 3, the index where 12 was found. This demonstrates the efficiency of binary search in action, rapidly narrowing down possibilities. In summary, linear search is simple and works on unsorted data, but is slow, O of n. Binary search is incredibly fast, O of log n, but requires sorted data.
Choosing the right search algorithm depends on your data's properties and the performance requirements. If your data is static and sorted, binary search is almost always the winner. However, if your data changes frequently or is inherently unsorted, the overhead of sorting it first might negate binary search's advantages, making linear search a viable option. Understanding both linear and binary search gives you powerful tools to make informed decisions about how to efficiently find information in your programs. Keep exploring and happy coding.
And that's a wrap on linear and binary search. Nice work! In the next video, we'll explore hash functions. See you there!